Welcome back to Mechanical Design 1 course. We will continue with the materials and processes. General properties of metals. The outline of this presentation will be as follows. We'll talk about general properties of metals, cast irons, cast steels, wrought steels, steel numbering systems, steel alloys, aluminum alloys, and other alloys. Non-metals general properties, material selection, product analysis, case study, material selection charts, bigger picture, and case study 2. So under learning outcome, we want to see what is the main purpose. The main purpose is material selection. So this is the main purpose of this video and this lecture. What are our resources? We'll talk about variety of the resources, but when it comes to the main reference book, we have Appendix A, mechanical property data. So I suggest you to refer to the book, go to the Appendix A and try to discover this appendix, and Figure 217 Young's module, and finally Material Manufacturer's Handbook. Yeah, so these are the resources we have. Here you could see the figure 2-17. We have the Young's module in mega psi and gigapascal of different materials: steel, stainless steel, ductile cast iron, titanium, and others. And here you could see that similar graphs could be used to select a proper mechanical property and select a proper material. Yes. So you will become more familiar with similar charts and graphs in coming slides, but you see that how we could visualize mechanical properties of different steels and alloys and how we could select between them. So let's go through some materials. Cast irons advantages will be relatively low cost and ease of fabrication. Density is slightly higher than steel. It is weak in tension and high compression strengths. And carbon contents are between 2 and 4.5%, and not easily welded because of the high carbon content. It is not easy to weld them. Okay, so these are basically the general specification of cast iron. We have white cast iron, which doesn't have graphite, and we have gray cast iron, most commonly used form of cast iron. So graphite helps machining and casting, so that's why they are more common than white cast irons, because of the graphite that helps machining and casting. Okay, so it works like lubrication. Graphite is like a lubricant. Okay, so cast steels has much less carbon than cast iron. Mechanical properties superior to cast iron, but inferior to wrought steel. So it's better than cast iron, but let's say worse than wrought steel. We'll see what is wrought steel. Classes: we have low carbon, less than 0.2%. We have medium carbon, 0.2 to 0.5, and we have high carbon, more than 0.5%. Yeah, but anyway, it will have less than 2% carbon content. Wrought steel refers to all processes that manipulate the shape of the metal or material without melting it. So if we shape the material without melting, we call it rod. And we have two kinds of rod. Still, we have hot rolled and cold rolled. I suggest you to refer to the previous session and see what is the differences between hot work and cold work, mechanical process, to understand the differences between mechanical property of these two kind of rolled steels. And hot rolled steel change the shape at elevated temperature, and it has a rough surface. So this is basically what happens in hot working. Good choice for steel members used for building and machine frame construction. So making a profile of steel or iron is not easy to be done without hot working. Cold rolled steel changing shape at room temperature. Just the definition of cold working: very good polished surface, and steel strips, plates, round and rectangular bars, tubes, etc. could be made by cold working technique and cold rolling technique. Okay, steel numbering system. Here you could see that table 2-5 lists type of steels and the numbers of them based on AISI and SAE standard. For the carbon steel, plain and free cutting starts with 10 or 11. For alloys of steel, when it has significant content of, let's say, nickel, chrome, and other metals, we have specific numbering and starts, let's say, for nickel 23, for chrome 50, yes. And we have a detailed, basically, explanation and description of what should be the content of the metal to be classified on this specific series. Okay, so in this slide, you will see one figure and one chart. Figure 2-18 basically compares steel and alloys of steel tensile strengths. We had a similar graph for Young's module of steel, and these type of graphs and charts help us to select the proper material based on our need. You see that the plain steel has lowest strengths than other alloys. Here on this figure, you see that we have three alloys of steel. We have 1020 hot roll, we have 1095 hot roll, and we have 4142 quench. Please refer to previous lectures and videos and see what are the differences. You see that this one is more brittle than others, and this one is the most ductile one. And all of these alloys almost have same Young's module. Aluminium alloys. Aluminium is the most widely used non-ferrous metal. Low density, good strength to weight ratio, ductility, high conductivity, corrosion resistance, and reasonable price are its main properties. Alloys have significantly greater strengths and extensively used in aircraft and automotive industries. Table 2-6 of the book lists aluminum alloys, and you could see the numbering system. So aluminum with 99% content starts with 1. The alloys of aluminum that has significant content of copper starts with 2, and so on and so forth. Plus here, you see that hardness designations. Okay, so if the aluminum is just have the same hardness as fabricated or is annealed or work hardened, so you see that basically it has a different numbering system and designation. Other alloys, we have titanium alloys are among the newest of engineering materials. Magnesium alloys are lightest of the commercial metals, but is relatively weak. And pure copper is soft, weak, and malleable, and is used primarily for piping, flashing, electrical conductors, and motors. We have non-metal general properties in this slide. Polymers would be thermoplastic and thermosets, ceramics, compounds of metallic and non-metallic elements called ceramic, and composites, combination of strong fibrous materials such as glass or carbon fibers glued in a matrix of resins such as epoxy or polyester. Okay, so far we have studied mechanical properties. What is Young's module? What is yield strength? What is ultimate tensile strength? So on and so forth, yes? Variety of mechanical properties. Plus now we are kind of familiar with general properties of metal and non-metal materials. But now it comes to the material selection. So it's decision. Yes, we need to decide which material is the best for our design. So many materials and so much information. So how do we decide? How do we begin to choose? First, we need to look at the function of the product and product analysis. So we need to understand what is our product, what this product is designed for, and what do we need. Based on our needs and specifications, then we could go for material selection. Okay, so what is product analysis? Just what it says, analyze the product. What does it do? How does it do it? Where does it do it? Who uses it? And what should it cost? Yes, so what is exactly our population target, if it's going to be cheap or it's going to be luxury, expensive design and machine. So we need to already decide for the cost and the purposes. Okay, so let's go for one case study. The first one, it's a bike. And on the bike, we want to also do some analysis on a specific part, which is a bike frame. But first, we want to see what is the function of a bike. Is it obvious or not? You should basically answer this question, yes? No, it's not that obvious. How does the function depend on the type of bike? The bike is going to be a racing bike, touring bike, mountain bike, commuter bike, or child's bike. So you see that these categories only changes our design, changes our material selection, and it influences our design a lot. Okay, so now let's go for the bike frame only and see how we could analyze that and what material we could select for the bike frame. We could see the frame design detail in this picture, and we could go more specific on our case study, but for now we stick to the general purpose of a frame and selection of material for the frame. So for this case study, we want to see how is it made to be easily maintained. Yes, so the bike, is it made to be easily maintained or not? What should it look like? Colors, etc. Yes, so static, basically, properties. What should it cost? How has it been made comfortable to ride? And how do the mechanical parts work and interact? So lots of questions we could list. There is no any specific framework or let's say template. You should think of do the brainstorming, list these questions, and see how the answer of these questions could influence your design. Okay, so when we analyze the system, we need to break the system down into individual components and then analyze each one. The bike breaks down into various parts, yes, frames, forks, wheels, saddle, etc. But now our focus is the frame. We need to look at the following for each part: requirements, mechanical, ergonomic, static, etc., function, how many are going to be made, what manufacturing methods are we going to use. So this manufacturing method sometimes overshadow all the above questions. And manufacturing, oh no, we have to actually make it, yes? So we have to go through the manufacturing process. So we need to choose a design and select a proper material so it could bear that manufacturing process. And that manufacturing process should be suitable for that design and part, yes? Sometimes it's not possible to really manufacture specific frame based on our design, based on our machine we have in our factory. This is a key question which has a massive influence on material selection. For example, the frame, what materials could we use? Yes. So some materials are not proper because we need, for example, to do welding, and welding cannot be done on some materials, doesn't have proper strength, so on and so forth. Okay, so for example, for the frame materials, we could think of steel, which has strong, stiff, heavy, but is cheap. Aluminium is weaker, lighter, but more expensive than steel. Or we could think of composite, strong, stiff, very light, but expensive to buy and to fabricate. So we need to have a strong or stiff basically material. So we need to think of these materials based on our design needs and doing trade-off between cost, between strengths, and see which one is the most suitable one for our design. Okay, so what mechanical properties do we need? Strengths, modulus, etc. So we need to list them and come up with the range of the strengths or Young's module that we need. How could we determine this? You will see in the coming chapters and to video sessions, you see how you could basically choose or find a proper range of strengths or modulus of Young and etc. Yeah, physical, what density do we need? What melting point do we need? Electrical conductivity, resistivity, static properties, appearance, texture, color. Is it important to have a specific type of appearance or not? Based on our needs, is it going to be a cheap bike or a luxury bike? And based on that, we need to think of these properties. Processability, is it needed to be ductile? And should it be a mold? Should it have a mold ability or not? And the last but not least, which is very important, is cost. Yes, so we need to think of the cost and see what should be the cost range of our final design. So where do I find the data? Yes, so for example, now you thought of your design and you know that you need these specific properties. Where you could find a proper data set. You could find those in textbooks, data books, manufacturers, literature, or manuals, or internet sites. Textbooks, they are good for general information. Some have tables of properties. They're not good for detailed specifications and properties, and they are a useful first point of call. Okay, so we should think of that when we refer to textbooks. Okay, they are not good for detailed specification, yes? So it's good as starting point. Textbooks are a good starting point. And that's why we always refer to our textbook, the main reference book for mechanical property. But when it comes to the real design, you need to also refer to other references. Data books, one of the quickest sources of detailed information. So we have detailed information, usually contain grades and specifications as well as properties. Small and perfectly formed pocket books. So we have some pocket books, small and perfectly formed, to find those detailed informations, and they are easy to navigate around. Manufacturers' literature or manuals, variable in quality and usefulness. So some manuals are good and they have high quality. Some of them are low quality, often only cover their products, which is still good when we want to buy a product from that specific company. So we want to know more about that product. Usually do not compare materials. Can be subjective, yes. So can be subjective. So we should be careful. And they are good for final selection before ordering. Okay, so it's good for final touch. Internet sites, lots of poorly presented information. We should be very careful when we refer to internet sites. We must know what is that site exactly, or what information is presented on that site. Otherwise, we could end up having lots of poorly representative information. Google searches bring up lots of rubbish. Yes, so be careful. You cannot just randomly Google search and blindly open one website and extract mechanical property. You must know what is that site, and if that site is a manufacturer website or not. And that's very important. Hard to find technical information, so it's very confusing. It's not filtered. and best to use non-commercial sites. Yes, so sometimes commercial sites basically are full of advertisements and are confusing, misleading. So we should be very careful when we use internet sites. Okay, so now material selection charts. If you refer to those resources, you could see these type of material selection charts. So in Appendix A of the book, you could see these type of charts. This one is extracted from the reference book. You see on the x-axis we have density, and on the y-axis we have Young's module. So it is designed for selecting selecting a material based on Young's module. Here you see we have foams, rubbers, polymers, so weaker or softer materials, wood and wood product. Then we will go to stiffer products, composites, porous ceramics, metals and alloys, and ceramics. Yes. So these are very useful when you know what Young's module you need. So you already have done analysis and you know what Young's module you need, what density you need, let's say for your design. So you refer to these type of charts and see what broad category you need and where you should select your material. Should it be a metal, or should it be a composite or polymer, and etc. Okay, so here again from the book we have density and the Young's module. So Young's module versus density here. More detail on each category. You see, for example, here for the metals, we have tin alloys, copper alloys, nickel alloys, and a variety of the alloys, and more subcategories here could be found on this graph. Again, with the same purpose of selecting material. Here we have strengths versus density. Again, if we know what the strengths do we need, then we could refer to these type of charts and see what the broad category of material we need. Is it metal? Is it the polymer? Is it basically foams, and etc. Yeah? So we could select material based on these charts. At least for the start, we know, do we need ceramic? Do we need, let's say, aluminum alloy? And then inside aluminum alloys, do more research and select a proper one. Modulus density chart that we already watched. Modulus spans 5 orders of magnitude from 0.01 gigapascal for foams to 1000 gigapascal for diamond. Okay, so huge range. It's a huge range. The charts therefore use logarithmic scales where twice the distance means 10 times. Okay, so we have a logarithmic scale to cover the whole range. So please refer to those charts and see what do we mean by a logarithmic scale. This makes it possible to show the full range on one chart. Again, on material selection charts, they allow easy visualization of properties. They show lots of different materials, can be drilled down to specifics. So you saw, for example, we had metal category, and then we have tin alloys, aluminum alloys, chrome alloys, and etc. Show balances of properties and ideal for a first rough cut selection. First basically rough cut selection. What do we need, wood, or do we need ceramic, or do we need a metal? Okay, you should always look at the bigger picture. Okay, so don't get lost in details of your design. Always back and see what is the bigger picture of your design. Is the product performance driven or cost driven? This makes a huge difference when choosing materials. So which of them basically has more priority, or you want to keep a balance? Yes, so you should know this and keep that in your mind when you're selecting your parts and materials. Manufacturing process, so don't forget manufacturing process. Although we usually choose materials first, sometimes it's the shape and process which is the limiting factor. Okay, so sometimes the one specific shape uh, cannot be found in other type of alloys or materials. So for example, here on this profile of aluminum, it's hard to find same profile with the same shape in steel. So if we need that specific profile, then we somehow need to change our design to choose aluminum. Okay, so now let's move on to the case study 2 for a green container. And on this one, please think more yourself to see what are the requirements and what you need. I will go through that quite fast, but when the slides finish, try to think yourself what are the requirements for a green container. Okay, so should be these ones. So should provide leak-free environment for storing liquid, comply with food standards and protect liquid from health hazards. For fizzy drinks, withstand pressure, okay, because of the gas, yes, brand image and identity. Easy to open, easy to store and transport, and cheap for high volumes. Think about more basically specifications, yes? What are possible materials still? Aluminum, glass, plastic, and paper. Now between them, you could think of how you could choose one broad category. Glass, see if you could basically satisfy your specifications, or aluminum, still, what strengths do we need to basically satisfy those requirements for the manufacturing? What Young's module do we need? Does it need to go through a cold working, hot working? And based on that, we need to select. Okay, so this slide will be the last slide on the mechanical property and material selection. The next video, we'll move on to a new topic.